Hello everyone. So Spartificial is launching its project series on YouTube, which gives you an opportunity to not only learn but explore as well as work on some amazing projects which are based on artificial intelligence through every videos we'll be uploading in this series, where each video will take you through all the necessary information to get you started with the project by showing one of the approaches towards how we can tackle the given problem statement in that particular project. And at the end of every video, there will always be some interesting challenges or tasks waiting for you, which if you complete and submit, you will be getting certified as a part of reward for all the hard work and time you are putting into it. And this is how it's going to work. Every project video that we'll be uploading in this series, it will have a unique project ID and name given to it, which you will need while filling the Google form to submit your work. And this form link can be found at the end of every notebook which will be used in the videos as well as in the description box of that same video. And I welcome you to this first video of this series where we'll be going ahead and hunt for exoplanets in this vast mysterious cosmos through machine learning. So this is your project ID for this video, and that is HEML0922, and its respective project name is given as Hunting for Exoplanets with Machine Learning. And as I mentioned earlier, you will be needing this information while submitting the Google form. And just to avoid any kind of confusions, I will also be demonstrating how to use this information and upload it in the Google form. But for now, let us go ahead and dive into the world of exoplanets. So if I just click on this link, it will redirect me to this particular PowerPoint presentation where we'll be finding and discussing all the information regarding exoplanets, its history, and what are some current methods we are using in order to detect exoplanets. So let us begin. So what do we mean by the term exoplanet? In simple terms, any planet that wanders outside our solar system can simply be considered as an exoplanet, and they are detected by astronomers by observing the intensity of their parent stars, where parent stars are the stars around which these exoplanets orbit. Exoplanets are made up of elements similar to those of the planets in our solar system, but their mixes of those elements may differ. For example, some planets may be dominated by water or ice, whereas others are dominated by iron or carbon. Also, exoplanets come in a wide variety of sizes, ranging from gas giants larger than Jupiter to small rocky planets about as big around as Earth or Mars. In the 16th century, the Italian philosopher Giordano Bruno suggested that the distant stars were similar to our Sun and therefore may harbor planets of their own. And now coming on to the history of exoplanets. Early claims to have detected exoplanets were made in the 19th century, notably by William Jacob. In 1855, he saw deviations in the orbits within the nearby 70 Ophiuchi binary star system. The first time we actually detected an exoplanet was in 1917, and it was done by NASA's Jet Propulsion Laboratory, but it wasn't confirmed. The first planet orbiting a star similar to that of our Sun was found in 1995. The planet was half the mass of Jupiter at least and no more than twice its mass. Now we are living in the era of exoplanets. The count of confirmed planets is in the thousands and it keeps on rising. That's from only a small sampling of the galaxy as a whole. The count could rise to the tens of thousands within a decade as we increase the number and observing power of robotic telescopes launched into the space. So now comes, why do we hunt for exoplanets? Observing exoplanets allow us to determine whether we actually understand those processes even in our own solar system. In fact, what we have seen so far is that most solar systems do not look like our own solar system. What finding exoplanets does for us is open up a vast exploration area to look for other habitable worlds, and it has upped the likelihood that we are not alone. So what are some methods available in order to detect the exoplanets? So these are the 5 methods available, naming radial velocity, microlensing, astrometry, direct imaging, and the transit photometry. So we are going to use the transit photometry for this particular project because this is the method through which we have detected the most amount of exoplanets till date. And because we are going to have a larger data, so it does make sense that we are going to use this particular method in our project. So coming on to this technique a bit later, and let us discuss about all the other techniques in a very quick manner, so that at least you get an idea about, okay, yeah, this kind of methods do exist and how it works. So in radial velocity, what we look at is, we look if a particular star is wobbling in space. Now this kind of wobble is because of any kind of an object orbiting it. So if an exoplanet is orbiting around it, this star would wobble around its particular position in space. So even if we talk about our sun, for example, so because there are some planets orbiting it, sun is also not stationary, it's continuously wobbling around the space, and because of which we know that if this kind of pattern is observed in any stars, then it must have an exoplanet orbiting it. Similarly, in astrometry technique, we are again studying this wobbling pattern, but now we are comparing it with the other stars nearby this. And if other stars are not wobbling, and if this is the only one star which is wobbling, then we can confirm that, okay, yeah, there must be an exoplanet around its orbit. And then coming on to the direct imaging technique. Direct imaging technique is simply taking the photograph of an exoplanet. And the recent example is the James Webb telescope. It recently took the direct photograph, and that's the recent example, so I just thought to mention it. And coming on to the micro lensing, as the name suggests, it uses the gravitational lensing in order to understand if a star is having a particular exoplanet orbiting it or not. And now coming on to the transit photometry. So what happens over here is, there are some space telescope out there in space, as the name suggests, which is continuously monitoring the values of brightness of the stars around it. And if these brightness values are having some kind of dimness continuously seen as a pattern over time, then we can say that, okay, this star must have an exoplanet because of which there is some kind of dimness. So how this thing works? So whenever we are having a star, and if we pass something in between our telescope and the star, it's obviously going to cause some kind of a dimness in the brightness, right? And that's the reason why we say that, okay, there must be some kind of activity going on, something which is orbiting that planet, and it must be an exoplanet, because of which we are getting this continuous pattern in our light curves. And these kind of curves which we obtain are also called as light curves. So we are going to deal with this particular technique, and again I will be explaining this when we will be looking this particular pattern in our data set. So these are some methods through which we can detect the exoplanets. And we are going to use in this project the Kepler Space Telescope data to detect the exoplanets. And this telescope basically uses the transit photometry method, because we are going to have the values of brightness, and based on that brightness we are going to identify if that particular star is having an exoplanet or not. So that's a basic idea about what we are going to deal with this project. Let us now go ahead and explore this exoplanet dataset. And we are going to deal with this Kepler Space Telescope data, and this is how it used to look like. Isn't it just beautiful and incredible at the same time? Anyway, for now let me just go ahead and click on this link, and it will redirect us to this particular web page of Kaggle, where we will be able to find all the necessary information about this dataset. So this data is describing the change in flux, or the change in light intensity of several thousands of stars, where each star is having a binary label to it of either 2 or 1, where 2 is indicating that the star is confirmed to have at least one exoplanet in its orbit, and some observations are in fact multi-planet systems. Well, these lines are basically indicating that this is the problem of a binary classification, where with the help of the values of brightness of a particular star, we are going to identify if any exoplanet is orbiting around it. By which method? With the help of transit method we just looked into our PowerPoint presentation. Well, this is some more information which you can get about this dataset. If you want, you can just go ahead. I'll be providing this link over here in the same notebook itself. So if you just click on it, it will take you to this particular web page where you can find all this information. For now, I'll just copy this link so that we can add this in our kernel. And these are some steps through which we can add this data in this notebook. So if I just click on this arrow on the top right of the screen and just copy and paste this link over here, it will fetch this data set for us, and I simply need to click on this plus icon now, and it will simply add this data set for us in this notebook. And we can see that the data has been added, and we are having two files, and both of them are in CSV format. One is for training and one is for testing. So we have successfully added the data set into our kernel, and now we are just going to import the most needed libraries, starting with pandas. So I'll import pandas as PD to read the data frames or to create data frames because we are having the CSV file, and I'll also import cbond as SNS because if we want we can also use some kind of statistical plots. Also numpy and matplotlib, import numpy to deal with any kind of arrays, and also the matplotlib, import matplotlib.pyplot as plt to just beautify our plots. Also I personally prefer using 538 styles. I'll also use it, so plt.style.use, I prefer 538. I also use dark background a lot, but for machine learning projects I personally prefer 538. So because Kaggle also throws some warnings now and then, I'll also import warnings and simply filter it out and ignore it. So warnings dot filter warnings, I'll simply ignore it. Okay, so this is how we can ignore any kind of warnings that Kaggle will throw in our output. So it's just a very disturbing thing. Anyhow, so let us now go ahead and get into the data set. So let me create a trained data frame, and because it's a CSV file, so let us create a data frame with pandas and read CSV file, read CSV, and we can directly get the path of this file by clicking this arrow over here, and this is our training data. So I'll just copy this path and add it over here, and let us see the first 5 data of the stars we are having. So train df.head, and it's going to print out 5 data points for us. So let us see what do we have. So as we know, here are the flux values, or we can see the brightness values on the different time intervals, and we are also having different labels to it. Right now we can just see 2, which means that these stars are having the exoplanets in its orbit. Well, so yeah, this is how the data set looks like as of now. So now what we can do is we can just simply go ahead and check the overall shape of this data, right? So we can do it with the help of train. It's always a good practice to have, like, comments whenever I'm writing any kind of code. So let us just write shape of the training frame, and we can get it with the help of train df.shape, and if we run this, we are going to identify it as there are a total of 5087 stars, and there are 3198 values of the different fluxes given to us. So I've also written the summary points for us that we can understand that this data is based on the transit method for detecting exoplanets, and there are a total of 5087 stars in our data, and for each star we are having 3197 flux values. Well, because one column is also for the label, right? So if we just skip this, there are a total of 3197 flux values at different time intervals, and these flux values are used to plot the light curves, as we saw earlier, to detect if the star is having an exoplanet around it or not. So we can also visualize this. We'll be coming on to this a bit later, but now let us go ahead and check for any kind of missing values in our data set. So we can just say that display the rows with null values in our data frame. So train df, because that's what we have given the name. Inside this train df, what I need is there any kind of null value, any in x is equals to 1, and this is probably going to give us the rows with the null values if it is having at all any kind of null values. And we can see there are no rows, so it means that our data set is very much neat and clean. We don't need to have any kind of we don't have to use any kind of techniques to fill up these missing values because we don't have any. So what we can do is we can just call hitmap from cbond, so SNS dot cbond or dot heatmap and simply get null values from the training data frame. So train df dot is null, and if I just simply plot this, it's going to give me an idea about how many null values are present, and if it's present it will show some kind of dashes on the plot, horizontal lines, or else it will just give me a blank plot. I'll just write a comment over here, display null values in train data frame. So we can see that this plot is completely blank because we already know that there are no missing values, but just in case if we wanted to see, if we wanted to visualize null values, then we would have seen any kind of horizontal bars over here which would have indicated that okay, for this particular column on this value we are having this null value, alright. But anyway, so this is just a conclusion written over here, and because we cannot see any kind of lines in this plot, we can conclude that there are no missing values in this data. And now let us just decode the labels in this data set. Like we don't know, like where are the stars in this whole data set where it can have an exoplanet around it, and where are the stars where it cannot have any kind of exoplanet around it. So let us just figure it out. So first of all, I will just find out how many labels are there, although we know that there are 2 labels. So but how can we check it? So check how many labels are present in train df. So we can do it by simply saying train df dot unique. It's going to give us all the unique labels, and I guess, oh yeah, there is some kind of a mistake. It just, yeah, okay, I don't know why. Oh yeah, I forgot to say in which column, right? So I am going to pass in the label column, and we can see there are 2 unique values, 2 and 1. And now let us just identify where are these 2 values situated in our data frame. So extract, I'll extract the index for the stars labeled as 2. So let us see where are all the values with the exoplanets are located in our data frame. So I can just say that I'll just create a list of train df, and I'll see where inside this train df in label column the value is 2, and let us see. Alright, so all these values are telling, but I'll just pass that I want index, right? So I'll just simply write dot index to get just the index values, and yeah, these are the index values on which we are having, and we can see it's a continuous like 0 1 2 3 4 all the way up to 36. So all the way up to 36 we can see that we are having the indexes of the stars which contains the exoplanets around it. So it means that all the other values apart from 0 to 36 contains the values, contains the data of stars without any kind of exoplanets, right? So this is a basic idea about it, and here are my conclusions, that there are a total of 2 classes, one for stars with exoplanets and one without the exoplanets. And because there are very few labels for label 2, we can conclude that this label is particularly belonging to the stars with the exoplanets. And we can also visualize this count with the help of the count plot, again from the cbond library. So what we can do is, in order to visualize it, we can simply say that sns dot count plot, and simply pass in the label as the label, yes, and the data as train df, where anytime if you are just confused about what are the inputs we can pass to this particular function, you can just press shift tab over here and you can just see all the things which you can pass over here, okay? And all the description about this arguments can be found just by scrolling down, and it just works like this. So anyway, let me just plot this. So we can see that there are much more values of the stars with the label of 1 as compared to 2. So let us just beautify this plot a bit. So how can we do it? First of all, let me just add the figure size properly so that we can visualize a bit about how many stars are over here. So plt.figure, and I'll just give fig size, and let me just take a random value depending on how I want to make it look like. So 3,5 should work, and I'll also give axes to this so that I can also get the values about how many count of labels are there for 1 and 2 respectively. So I just want to display it on top of my bar. So what I'll do is, for that I'll say that axis dot bar labels or bar label, I want to see the values on top of the container. So containers, and I'll simply write 0, and it is going to label simply the values of the count on top of the bars. So yeah, that's all about it, and let's see how it works. Yep, now it kind of looks a bit more neat. So we are having total of 5050 stars with a label of 1 and 37 stars, which we also saw over here, right? There are total of 37 stars. If we count 0 until 36, it's total of there are 37 stars, which is labeled as 2. So there is a huge imbalance in our data, which isn't good for our kernel, and this is again explained later in this notebook, so I'll just not focus on this part as of now. And we'll need to balance it in using some kind of resampling technique, and we are going to use RandomOverSampler for this data, and we'll do that after building this model of this imbalance data set to compare the results. So what it basically means that I'll first of all train my data without handling this imbalance in the data set, and then I'll also show you the result after handling this data set by using the RandomOverSampler, and then simply compare this data, the result of this data, and see how well can we use this kind of resampling techniques to give beautiful outputs of our model. And now for the ease of our model, it is always better to feed in the data to our computers in terms of zeros and ones. So what I'm going to do is I'm going to replace my class 2 with class 1 and class 1 with class 0. In order to do this, there are again tons of different ways of doing it. So what I'll do is I'll first of all give the comment of replacing the labels, and I'll simply use dictionary method inside the pandas to replace it. So train.df replace, and I am going to pass in the column where I want to perform this replacement, and then what are the values I want to replace is what I'll be mentioning over here. I want to replace my 2s with 1s and 1s with 0s, and if I if I just want to see if I have successfully changed these values, what I can do is I can again do train df dot unique, or I should say train df dot label dot unique, and see if the unique values are changed from 2 and 1 to 1 and 0. So yes, we can see now our data is having the labels in terms of 1s and 0s. So we are done with this step, and now we can go ahead and I'll just delete this extra cell we are having over here and visualize the light curves in this data. So when a planet passes between an observer and the star, the flux value decreases, and hence we see the dip in the light curves, which is the confirmation that the exoplanet is orbiting around that particular star. And this is what we also saw in the PowerPoint presentation, and we call this as a transit method. So what we are trying to achieve is, I'll just scroll up and show you the data frame. So over here we are going to grab a particular random star, and based on the values of this change in brightness, I am simply going to plot this and try to obtain the curve which we just saw in this GIF. And if any particular curve is following this kind of trend, then we can confirm that that particular star must have at least one exoplanet in its orbit. So let me just try to show you what I'm trying to say over here. So I'm saying that I want to first of all drop the labels, because I can see that in my data frame over here I had an extra column which I don't want to plot. I just want to plot the flux value. So I'll simply drop this column first of all. And I also know that in all the values of flux, the values of time is like, with 1, 2, 3, 4, 5, 6, it is an integer number all the way up to 3197. So what I'll do is I'll simply plot these values from 1 to 3197, and respectively I'll be plotting its flux value. So let's see what is the kind of curve we obtain. So I'll just scroll down. So over here I'll first of all drop the label column, and just because I'm trying to plot this kind of data, I'm just going to create a new data frame named as plot.df, just a random name. So train df.drop, and now I want to drop which column? I want to drop label column, and I'll simply say x is equals to 1, else it's not just going to work, right? I just want to drop all the values in x is equal to 1 of the column label. So if I just do this and run this, I am going to get a data frame which is getting rid of any kind of labels, right? And now my task is to plot any kind of random star I want, any random star, and see how these kind of patterns do we get this kind of patterns, or what kind of patterns do we obtain. So because we know that in the first few indexes, that is from 0 to 36 index, we know that the star is containing at least one exoplanet in its orbit, and anything after 37 index, including 37, we are going to obtain a star without any kind of exoplanet. So let us just plot this thing randomly. So what we are going to do is, I am going to first of all take out the values of time. So I know that time is basically nothing but starting from 1 and it's going till 3197. So 3198 is what I will say, because I know that the last number range accepts is 1 more than what it should be. So if I just go ahead and check the last value over here, I don't need to scroll this. What I'll do is I'll just simply say what's the last value over here, and 3197 is the last value. So we are good to plot this. So on x-axis we are having range from 1 to 3198, and on y what are we having is, I'll just show you what are the values of y, right? Let me just grab any random star with planets first. So let us just grab the third index, and if I grab third index, what do we get? Let's just check. So if I'm saying plot df, I want the location, so I'll just say index location of third row and grab all the columns and get me the values in terms of array. So if I do this, I will be getting all the values starting from 3 to 6.52 all the way to 13.98 of this particular star. So you can see that it's starting from 3 to 6.52, and if I just scroll right for this particular column, we can see that 13.98 is the last value. So we have just grabbed all these values, and we also have the time values, and what we can do is we can just replace x with time and say this is the flux values, and I'll also comment this out that I'm trying to plot a random star from the plot data frame. And if I now simply use plot plt.plot and pass in time and flux value, and let's see what do we get. Yep, so you can see that we are getting multiple deeps over here. So it may be the result of multi-star system, multi-planet system, that's what I should say. Around a star there is a multi-planet system, and this is the kind of pattern we are obtaining. I'll just try to make it look a bit smoother. I'll try to decrease the line width, and let's line width is 1. Yes, it is looking much more cleaner now. And now what I can do is I can simply also just increase the total width of this diagram. So I can just simply say plt.figure and say fig size is equals to, let's say 15,5. Yeah, this is looking much more neat. And now what I'll do is I'll simply just also grab some other values of stars. Let's say any star which is having exoplanet, let's say 13th index. What do we have? Yes, we are still having this kind of pattern, we can see, right? We are getting this kind of deeps. And now what about some stars with no exoplanets? And let me take any random value, and let's say I'm taking 98th position star. What do we have? Okay, we can see this is kind of a straight line with some kind of we are getting some kind of outliers, where we can see this is an extreme outlier, and this could be a problematic thing for us, and we need to just treat this kind of things, and I'll talk about it a bit later. But right now let me just take any one more example. Let me take 198. Let me see 198, what is happening over there. So in the 198th index, the star is going to have this kind of pattern. Again, we can see there are high spikes over here, which we will have to treat, else our model is not going to perform well. And we are also going to visualize this with the help of box plot, that our normal range is in between let's say -500 to 500 somewhere, and these values is like at 1 to 50. So these values I just don't want it in my final answers. So what I can do is I can still just try to plot one more, and let's say I'm choosing one, or let's say 2000 some kind of star, 2998. Let's try to plot this. Yep, we can see that these values are just not required. So what I'll do is I'll simply now go ahead and say that we can see the random huge spikes, especially in stars without exoplanets, which can be considered as an extreme outliers. And because we are going to use KNN, and I'll also explain why are we choosing KNN. KNN can be sensitive to outliers, which is explained later in this notebook. So we'll have to handle it, and we can also visualize this with the help of box plot, as I mentioned. So let us go ahead and try to plot box plot and see what kind of thing do we obtain. So what we can do now is I'll simply scroll down, and over here these are all this observations written by me after going through this. So what I'll do is I'll simply plot these outliers, and let me just do it with the help of let's say first 4 index. So what I'll do is I'll say for I in range of let's say 1 to 4, what I want is I want to make a subplot. I want to plot multiple box plots together. So I'll simply say plt.subplot, and because I'm choosing 4, 1, 2, 3, so I'll simply say I want graphs on 1, 4, and I just want to pass the indexes from 1 to 4. And let me see what happens next. We want box plot, so sns.boxplot, and in box plot I want to pass in let's say train df as my data, and over here I'll just simply write the x values as the label and y values as I just want to say y values is equals to the flux dot, and I just add the index which I am trying to see. So I'll just say it's a string and then the index for what I'm trying to look at. And if I now just simply plot this, let us see what do we get. So I'll just have to adjust the size of the figure. What I'll do is I'll simply say over here plt.figure fig size is equals to 20,9, and let's see now. Yep, we can see the extreme outlier values, right? And these values are let's say around more than 1.25 e power of 6. So we need to treat these values and we need to just get rid of this extreme outliers, because over here we can see these outliers following some kind of a pattern, and we can not directly eliminate this. So what I'll do is I'll simply go ahead and eliminate these outliers, and the way through which we can do this, first of all I'll just go through these observations. So we can see that the flux values that are more than 0.25 10 power of 6 are extreme outliers. We can either drop it or replace it with the values of the highest value of the upper bridge basically. And for this use case I'm simply going to drop it, but if you want to try ahead and go for the upper bridge, so you can, this is the formula which you can use and directly replace these values with this upper bridge values. But right now for this use case what I'm going to do is I'm simply going to drop these outliers. So I'll simply write dropping outliers and say that train df dot drop, and now what I'm trying to do is I'm going to drop what I'm trying to do is now I'm going to go ahead and train df, and inside this train df I know that all the values which are with corresponding to these values, what I'll simply do is I'll do for one value and it will automatically do it for all the random values present in this particular data set. So what I'll do is I'll simply say train df, and I'll grab any random column of flux or row of flux, let's say flux dot 2, and if the value is greater than 0.25 e power of 6 or e6, I am simply going to get this index. There is a mistake I have done over here, that is I am going through train df. Inside this train df what I want to look at is what I want to drop. So inside this I need to pass train df over here, and now it's going to make sense. Yes, And now what I'm going to do is I'm going to take index and simply drop it, right? And I would say, because I want to drop all the values in this particular axis, so I'll say axis equals to 0 as well over here, and I'll also mention that in place equals to true, so it works without even saying train df equals to, right? So that's the same thing as saying train df equals to this thing. So if I just go ahead and work this out, what I'll be getting, let me check. I'll simply again plot this sns.boxplot, and let's say data is equals to train df, because that's where we did this kind of thing, and again x is equals to label, y is equals to flux dot, and I'll just simply do one very interesting thing. I would just take a random index, so I'll import random library first of all. I'll say import random, or I'll just use numpy to do it, okay? So string, and let's say I want np numpy dot random integers, that is randint, and then let's say I want any number between 0 to 1000, and if I just simply plot this, so see what we get over here. We are getting a random number, we are getting from the we are just plotting any random values of flux, and we are seeing that the higher outlier, the extreme outlier has been gone, right? It's not there anymore. So what we can do is we are good to go. We can just now go ahead and try to understand what is KNN, why did we choose KNN for this task, and how does KNN work, and some process of KNN. So now let us understand that why actually are we choosing KNN for this task and not some other classifiers, let's say like random forest classifier, XGBoost classifier, or for that matter any classifiers that are using decision trees, because we know that these kind of algorithms are actually robust to outliers and imbalance in the data set. We know that this data is having outliers as well as it is highly imbalanced. Then why aren't we choosing a method or an algorithm which is robust to these two things? Why did we end up to KNN? Because it is sensitive to these two things. So why are this sensitive to outliers and imbalance in the data set? It all boils down to the mathematics, or how is this algorithm constructed. It all boils down to that. So for that I'll be explaining you in a little while that why KNN is sensitive to outliers and imbalance in the data set. But for now, why are we choosing KNN as compared to the techniques which is robust to outliers and imbalance in the data set? So a very simple answer to this is, a good ML engineer is not going to just stick to a particular model or algorithm. Instead, what they do is they first of all clean the data set based on what is the task they are performing, and then they choose particular models which they think are going to perform very well, and then they feed this clean pre-processed data onto all such models, and they simply compare which model or algorithm is performing the best, and then they simply extract that model and just perform some hyper parameter tuning or some kind of task which is going to enhance the output. And that's how we choose a particular model or an algorithm, and that's exactly how we have got onto KNN. I have already applied this clean data after, it's not exactly clean, but after handling outliers, I have already applied this data on other models like let's say linear or say logistic regression, XGBoost classifier, random forest classifier, but all were performing nearly the same, and KNN, after treating this imbalance in the data, was performing slightly better as compared to all the other models. Well, we could still do a lot of things in order to improve this model. Well, that's one of the tasks which we are going to perform, but I'll be coming on to that a bit later. So what is the reason we are choosing KNN for this task? First, because it was performing one of the best as compared to all the models that were there in my mind, I have taken this. Second, it is one of the simplest ML algorithm based on a supervised learning technique. What is a supervised learning technique? That we are having some kind of a label data onto which we are going to train our model. So because it is one of the very simplest algorithms, we are choosing it. And these are some basic reasons because of which I think KNN is a suitable candidate, so that I can even explain that if there is outliers or imbalance in the data set, then how can we handle it, and how can we just see that, how can we compare the results without creating outliers or imbalance in the data set, and how can we compare it later, and what is the difference between them. In order to explain all these points, I am choosing KNN for this particular task. And I hope this is clear to all, because this is very much necessary to understand that why KNN and not some other techniques for this particular video. So coming on to the next point, that how actually does KNN work? We know that why are we choosing KNN, so now it's our duty to understand how does KNN work. So simple answer to this is there are only 5 steps, because I already mentioned that KNN is one of the simplest ML algorithms. There aren't much more steps to it. There are only few steps. So let us understand it step by step. So the first step is, in our model we are adding a data point. Okay, in our model we are already having, let's say, 2 classes for us. We are just going to consider a binary classifiers as our example, because it's going to become much more complicated if we add much more classes to it. Okay, so let us assume that there are 2 classifiers, 2 classification labels, let's say 1 and 2, or green and red for this example. So after adding this data point, it's going to ask which class does it belong to. Does it belong to red or brown or green? Then it's going to find the nearest particular neighbors. Now this is up to us. How can we choose this? And then it's simply going to go through all the possible points and going to choose the 5 nearest points to it. And then it is simply going to say that, okay, so in my 5 nearest neighbor circle, I only have 2 brown or red neighbors and I have 3 green neighbors. So there are, because of more of 3 green labels, it is saying that I must also be a green label. So this is how KNN actually works. Out of these 2 classification or classifying labels, it is going to choose any one of it based on nearest neighbors, and out of these nearest neighbors, which one are dominating, and it will itself classify it as that dominating label as compared to the other label. So that's what we are seeing in this GIF. So just to go it a very point by point manner, first of all, what we are going to do is to select the number of neighbors out of which we are going to choose. Okay, if I am going to classify myself based on 5 neighboring points, 6 neighboring points, or 7 neighboring points, it's completely up to us. K can be as high as possible. It's anything which you want to choose. It could start from, let's say, 1 and can go up to, let's say, 100, 10,000, whatever you want to choose. Okay, so now what happens is we calculate the Euclidean distance, or Euclidean distance is basically nothing but distance between 2 points formula, which we have understood in a chapter of mathematics in your high school. That is basically under, I guess, Cartesian coordinate systems, where we understand how can we find out distance between 2 points, and that's a simple formula: x2 minus x1 square plus y2 minus y1 square, and if we just take the under root, we simply find what is the displacement of these 2 thing, right? So coming back to this particular step, so let's say that we are choosing particular neighbors, and for this example we are choosing 5 neighbors. So now what this algorithm is going to do is, it is going to calculate all the distances for all such points available to us, and is going to identify which one is the nearest 5 data points, and then it will just keep a count of it, that the one which is having the highest amount of class, and that point is going to be classified as that class itself, as we are seeing over here, that because in this 5 nearest neighbors there are 3 green class and only 2 brown class, then this particular data point should belong to a green class. So that's how KNN works. And let us now look into what are some different ways KNN uses in order to calculate distance between any 2 given points, out of which we have already looked into a particular distance, that is the Euclidean distance, which is nothing but the shortest distance between any 2 given points. But is this the only one way to measure the distance between 2 given points? The answer is no. And as you might have guessed, that we can see that there is an alternate path which goes from the starting point to the right, and then from here till the ending point. So what we can do is we can also calculate the distance from this point to this point, and the distance from this point to that point. And if we add these distances together, we can still get distance from point 1 to point 2 in this particular way. But is this the most famous one? No, the most famous one is the Euclidean, where we can simply find the shortest distance between 2 points, and this can do a wonderful job. and hence we are also going to use this particular weight in order to calculate the distances in our KNN algorithm. And now comes how can we select the best possible value of k in this algorithm. So in order to understand this, let us first get an idea about what does this k represent. So let us just scroll a bit upwards. Over here we are choosing the value of k as 5. So what does it signify? It simply tells that whenever I am adding a new data point in this data set, it's going to compute a distance from that particular point to all the available points in this data. And then it's going to compare from the nearest k neighbors. So this is what the value of k means. I am going to compare my nearest 5 neighbors, and then out of this 5, which class is the most dominant one, and then I will simply classify this new data point to be part of that same class. So that is what is signified by the value of k. It simply tells that out of how many nearest neighbors do we need to make this kind of comparison. And I hope that you have now understood what is the value of k signifying. And now let us just go ahead and look into these points. So there is no sure shot method through which we can find out the value of k. We just need to do some trial and error in order to get the best possible value of k for our algorithm. And I'll also implement a particular way through which we are going to try out some different values of k with the help of for loop, and we are going to observe a particular trend that how my model is performing for different values of k. And by observing the trend, we are going to select which one is going to be the best for our model. So right now it might seem a bit confusing, but when we implement, you will get a better idea of it. So let us now continue. Usually we prefer the value of k being 5, but that's not the optimal way that this is the only best possible value of k for your algorithm, but usually people try to prefer the value of k as 5. Now what happens when the value of k is very low, like let's say 1 or 2? So here we can lead to the effects of outliers in our model. So what do we mean by, how can we say that lower value of k will affect the outliers? So what happens is, here is the diagram which completely explains on the left. So let's say that we are having a data set in which we are having 2 classes, one for blue class and one for yellow class. And this is what is the outlier, where we can see some points of blue class is coming in the area of, like let's say yellow part, right? It's coming a bit towards yellow side. And now if I am going to add a new point over here, and let's say I'm choosing the value of k as a very low value, let's say I'm choosing k is equals to 2. So what will happen is that over here this point is going to have a nearest neighbor of these 2 blue points, and it's going to consider that okay, I am also belonging to the same blue class, whereas we can see that it's belonging to the yellow class. So this is what happens when the value of k is low. We can see there is some kind of effects of outliers over here. And now if we just scroll a bit upwards, what happens when the value of k is high? So this can lead to the biasness towards the imbalanced data set, and this is what we are going to look now into this right diagram. So let's just choose a random value of k as 10, and in this imbalanced data set what we are seeing is the blue data set is pretty much higher as compared to the yellow data points. And now if we just add a new data point over here, and if the value of k is 10, so what is going to happen is it's going to choose some points which are nearest from this blue points more as compared to the yellow points. And because of this result, we can see this kind of biasness towards this blue data points, and hence this new point will be considered to again be a part of a blue class instead of a yellow class. So a higher value of k is going to be biased towards the imbalanced data set, and that's what we meant when we earlier said that KNN is sensitive towards the outliers and is also biased towards imbalanced data set. So I hope now you have understood the idea about why is KNN sensitive to outliers as well as biased towards the imbalanced data set. Let us now discuss some of the advantages of KNN. As we just saw that it is one of the simplest to understand, and in just a while I'll also show you the implementation, and because now you understand the mechanics of this algorithm, it will be even more interesting to see how we can implement it in Python. And the second point is, depending on the value of k, it can be robust to the noisy training data. So as we saw over here, if the value of k is very low, it can lead to the effects of outliers, and if the value of k is pretty high, in that case it could be biased towards the imbalanced data set. So if we are choosing k value pretty well, then we could ignore the effects of outliers as well as the imbalance in the data set. So that's also one of the advantages. But at the same time, choosing these values of k might be pain, and that's why it's also one of the points in the disadvantage of KNN, that sometimes determining the value of k can be a complex task. Coming on to the third point of the advantages of KNN, it is saying that it can be more effective if the training data is large. So if you are having a huge training data, then our classifier is going to perform pretty well. That's what this particular point means. And we have already discussed about this disadvantage. Coming on to the next disadvantage, we know that because we are computing distances between all the data points to the given particular point, it's going to take a lot of computational cost, and hence this point says that high computational cost as we are calculating distances between data points for all the training data. So whatever training data we are having, we are computing all the distances as with respect to that particular point, and it can be time consuming if the training data is pretty large. So this goes hand in hand, and therefore we need to be really very careful when should we use KNN and when should we not. So that is all about the theory aspect about what KNN is, how it works, what are some ways through which it calculates the distance between 2 points, and then how can it choose the nearest neighbors, and how can it classify if it belongs to a particular class, and then what are some advantages, disadvantages, what happens if the value of k is very light or the value of k is pretty high. In that case, how can it lead to the effects of outliers as well as the imbalance in the data set. We have discussed about all these points, and now it's time to implement it all into Python. And the way we are going to deal with this is, we are going to first implement our KNN algorithm on this imbalanced data set itself, and then we are going to balance it with the help of a random oversampling technique, and then again implement our KNN algorithm on that balanced data set, and then we'll simply compare the results so that we can understand what happens if we don't treat our imbalance in this data set, especially on these algorithms which are sensitive to this such imbalance in our data. So without wasting any much more time, let us go ahead and start the coding process. So first of all, I'll extract all the dependent and independent features in different variables. So dependent features in this case is simply the label column, because it is dependent on how the flux values are changing over time, and therefore this flux value becomes our independent features. So what we are going to do is, we are going to start by writing a comment, extracting independent, that is my x, and dependent, that is my y, features from train data. And my x value of train is simply very similar to the plot df. I am simply going to drop label column, because everything apart from label column is what is my independent feature. So what I'll say is, I'll say train df dot drop, and which column I want to drop? I want to drop label column, and I want to delete all the values from that particular column. So I'm going to write x is equals to 1. And similarly, my y train, I don't want any flux values, I just need to extract the label column. So I'll simply write train df dot label. So it will just fetch me the particular column of labels and drop everything else. So if I just run this cell, and if I want to just visualize this, so if I write x train and y train comma y train and run this cell, we are going to see that the first part of this output is simply having the flux, different flux values of all the available stars we are having in this data, and then the later part is showing the y train values, where with the respect of this flux values for a particular star, we are giving label to it. So we are done separating the values of x train and y train, and now comes the important step. What I'll do is, I'll first of all get rid of this train written over here, because what I'm going to do now may confuse you. So what I'll do is, I'll take this x values and the y values, or in other words, I'll take this independent features and dependent features and convert it into train test split. So if I just show you this data over here, we are already having a test CSV file. So what we'll do is, we'll just keep this as an unseen data. Okay, we'll just talk about this a bit later. But right now what we are going to do is we are going to take this independent and dependent features and split it into train and test sets. So how we can do it? We can just write a comment first that I am splitting this data into train and test sets. And how can we do this? With the help of train test split available inside the sklearn library, we are simply going to do this. So I can just say that from sklearn dot model selection import this train and split, train test split. So how does this work? We can simply get our training sets and the test sets like this: x train x test, y train y test, and call this train test split method, and it takes in the x data and the y data that are the independent and the dependent features respectively. So I am going to pass x comma y, and it also asks for the test size or train size. Let's say I am choosing test size as 30%. So what does this mean? I am splitting my x and y data as 30% for the testing purpose and remaining 70% as my training purpose. So that's what this means, and I'm going to assign a random state of 0. Alright, you can choose any value you want over here, it really doesn't matter. And now what we are going to do is we are just going to import a standard scaler, because over here we see that the values of the flux really has no particular range. Some values are, let's say, around -500, some values go till 8000, right? So let us just, without disturbing the differences between these values, let us just scale down these values in between a particular value. So what we can do is we can scale this data with the help of feature scaling technique. First of all, let me just run this. We have splitted our data in the training and testing set, and now we are going to perform feature scaling. So again we are going to go into the sklearn library, and in the pre-processing we are going to import the standard scaler. So let us create this object scaler, standard standard scaler, and over here we are going to scale our x train set. So x train scaled values are simply sc.fit_transform, and I'll pass in the x train value, and then simply I'll do the same thing for the test scale data equals to, now I want to perform the same steps which has been performed on the training data set. So I'll not use fit transform, instead I'll use just transform and pass in the x test data. And now if I run this, let us just check what are the values we are having for the minimum and the maximum values in both the data set, for train and test, both of it. So if I write np.minimum of x train scaled data, and along with it the maximum value we can have in the x train scale data, let's see what do we have. So we are having the values going from -57 to around 59. And what about the test data? We can literally see that the values we were having, which were ranging from, let's say, around -500 to some kind of 8000, 9000, it's coming into this particular range without actually changing the gaps between the values. So we are scaling it in this particular method. So let's see about the test. So we can see the test is ranging from about -38 to +38. So we are good to go. Now we can go ahead and simply fit this KNN classifier model onto this training data. So we can just give a comment fitting the KNN classifier model on this data. I should write training data because we are having both the data, so not to get confused, I am writing train data. So from sklearn.neighbors, I am importing k neighbors classifier as KNC. So I don't have to write k neighbors classifier again. I'm just importing it as KNC. And then we can just choose a random value of k over here. Let's say k is equals to any number, let's say 5, 10, whatever it is. We are just going to see how it works, right? Because we know that k equals to 5 is the most frequent chosen value. So I'll also, let's say, choose k equals to 5. So I'll say that my KNN classifier is equal to KNC, and now I'll choose how much neighbors do I want to compare it with. So n neighbors equals to, let's say, 5, and then to tell our KNN that we want to use the Euclidean distance. So how can we tell it? We can say that metric to use is MINKOWSKI. We are going to use this metric with p value as 2. So this will implement the Euclidean distance method to find the distance between any two given points in this data. So I'll then simply fit the model. So over here what I'm doing is I'm choosing the value of k as 5. I'll just write this over here, choosing k is equals to 5, and now it's time for fitting the model. So fitting the model, KNN underscore classifier dot fit, and I'll pass the scaled values of x and y. So x train scaled comma y train scaled, and after this we also want to see the results. So for results, what I'm going to do is I'm going to say that from sklearn.matrix I want to import few of the things. I'll be importing confusion matrix, and then I also want to import the accuracy score and classification report. This is what I really want to import. I can also basically use ROC curve, AUC, ROC curve and AUC as well if you want. Okay, these metrics are enough to identify if our model is performing well or not. Okay, and now I will simply just go ahead and type some of my results with the help of print statements. That print validation accuracy of KNN is simply the accuracy score matrix which I have imported. So accuracy score, and it takes in the arguments of the y predicted as well as the y test. So what is the y predicted? We have to make this as y predicted. We haven't made any y predicted over here, so we'll just simply make what are the predicted values we are going to get. So after fitting the model, I'll just write this predicted values. So my y pred is equals to KNN classifier dot predict, and I'll simply write x test. I want to predict on this x test, so that's why I'm passing x test scaled data as the argument. And now coming on to this accuracy score. So what are these input arguments this function takes? It takes y true and y pred. So y true is nothing but the y test in our case, and y pred we just computed. And then I'll just leave a line and then print my classification report. So print classification report. In a new line, I'll simply paste it as classification report, and I'll just press tab to okay. So it is also going to take the same input arguments true and pred. So y test comma y pred, and now what we can do is we can go ahead and also plot our confusion matrix along with the ROC curve and area under the curve. Let's just do it. I'll simply copy paste this code because it's pretty long. If you want, you can just go ahead and read this thing, and if you're having any doubts in understanding why is a particular thing written over there, you can just comment it out on this particular video and we'll just get back to you as soon as possible. But for now, this is how we can plot the confusion matrix, and this is how we can plot our ROC curve and area under the curve. And if I just run this thing, but before I run it, I just see one thing, that we are giving a label to this plot, but we are not giving a legend. So I'll just write plt.legend. So it basically gives me the value of the AUC based on the false positive rate and the true positive rate. So if I just type over here plt.legend, it should work. And over here we can see that the accuracy of KNN is pretty much 99%, but we can see that the precision score, recall and F1 score is pretty much not well. It's not doing good at all. It's 0, 0, 0 for the class 1. And over here, even if we see in the ROC score and the confusion matrix, we see that there are no single predictions for exoplanet. It's 0 over here, and this is pretty very much bad for our particular classifier. And even the ROC score is simply 0.5. So what we can do is, we can now see we have already dealt with the imbalance data set. Now what we are going to do is, we are going to perform exactly the same steps what we did in the implementation part, but before getting our data, what I'll do is, I'll first of all perform the random oversampling technique to balance out the data, and then apply exactly the same steps with the random oversampler data, and then see after the balancing the data set between the classes we had, what is the output. For now we can literally see that our output is not doing good at all. For our class 1, it did not predict at all if the exoplanet is the true label, and if we are predicting the exoplanet, then we saw that the output is 0, and this is pretty bad. So believing that this model is a pretty good model based on the accuracy, so classification task based on the imbalance data set is really going to give the false kind of idea that your model is working very well. And that's why we need to check the precision, recall and F1 score over here with the help of classification report. So now let us go ahead and apply the random oversampling technique. But before that, if you just want to go ahead over here, this is just my confusion matrix, and the table on the right is basically showing us how we can calculate accuracy, precision, recall and the F1 score with the given formula over here on the right. But the basic takeaway over here is, the higher the precision, the higher the recall, the better your performance will be of your model, and the lower score would simply indicate that your performance is not up to the mark. So if we just scroll a bit upwards over here, we can see that for class 1, precision, recall and F1, all of this were 0, and that's how we could say that our performance was not at all good. It was really worse, and again this is because of the imbalance in our data set. So let us go ahead and handle it with the help of random oversampler. So what we can do is, first of all, let us just check if the x and y values which we had already created, if it's similar or do we need to change it. So yeah, the values have not changed at all. So we had created the train test split, but we did not touch x and y values at all. So we'll just keep it as it is and perform random oversampling on this. So first of all, what we need to do is, we'll go into the imbalance learn library, and inside it we can just call the random oversampler and simply perform the random oversampling technique. So what I'll do is, I'll start by giving the comment handling the imbalanced data using imb learn. So from imb learn dot oversampling, I am going to import random oversampler, and then I am simply going to call this method of random oversampler and say that its variable which I am going to use is random oversampling. It is equals to random, why is it not getting, random oversampler, and then I am going to create, let's say, x value with the ROS and y value with the ROS. It simply means that my x and y values are now randomly oversampled, and then say ROS dot fit and fit underscore resample. That's what we have to use, and it takes in the x and y data. So I'm just going to simply create the arguments of our x and y, and now we are good to go. And let's see if we are, yeah, it's running perfectly. And now we can just simply visualize this again with the help of the bar plot. We can say that y underscore ROS dot values count or value counts, and then simply plot this, and we will say that kind is equals to bar plot, and I don't want to give any kind of title or X label, and directly let's just see what happens. And we can see that the label 1 and 0 is now balanced. So let us now understand the intuition behind how does this random oversampler works. And in order to show it to you, what I'll do is I'll go ahead and say that from collections import counter, and I'm trying to print what are the values of counts of labels before and after applying the random oversampling, so that we can appreciate that okay, this is how the values have changed. So before applying random oversampling, what is my count of data without the random oversampling, and then in the next line I'll print what is the count after applying ROS, and I can get the value by using counter method on the random sample labels. So if I just see this, so we are having initially the data points for class 0 was 5049. However, initially if you remember from the count plot which we had got, there were 5050 values for class 0. But now where did this one value go? Where did this one whole data point go? It is because we were having the extreme outliers and we had dropped it. So it means that it was belonging to class 0, the outlier which we had removed, and therefore we can see that one of the value is dropped, and now we are getting the value of 5049 instead of 5050 for class 0. So we can see that before applying the ROS, there were 5049 data points for class 0 and only 37 classes or 37 data points for class 1. But after applying the random oversampling, we can see that the class 0 is still having 5049 data points, but class 1 data points have been increased from 37 till 5049. So if I just want to see how many extra data points we have added, so it is 5049 minus 37. If I run this cell, so we are having 5012 extra data points that we have added in this y in order to say that okay, now my y is balanced. So what we are doing in y ROS is we are simply adding the extra values of 1 in this y, so that our y label for class 1 increases from 37 to 5049. So if I just want to demonstrate or visualize this to you, what is happening, I'll first of all show you what is the length of y. So y is the data without applying the random oversampling. So we can see that there were only 5086 data points, and now if I just add 5012 data points to this, so it is giving me that now after adding the extra 5012 data points, your value should be, the total data points should be 10098. If we just cross check with what is the length of y ROS, indeed it is 10098. So what we are doing is in the y, when we were having 5086 data points, after that we are simply adding 111111 over there and increasing the value from 5086 to 10098. And if I still want to make you show this kind of a demonstration of what has happened inside the y ROS or y, so what I'll do is I'll simply go ahead and say that list of, I'll simply print this thing, okay. So I want to print the list of y ROS values, but only till first 5086 samples, because we know that initially 5086 data points was what we were having. And now if I simply go ahead and print this, you can see that initially we are having 37 data points of class 1 and all the other is for class 0, right. And now if I want to show you what is happening after this particular point, so if I just remove this and say 5086 and all the values after this in y ROS, and we are expecting that we have simply added the random values of class 1 into this particular array. So yeah, we can see that there is only ones over here. So we have added this extra 5012 data points which contains only class 1. So we have simply added this to our data set of y to create this YROS, and I hope now you have understood how does this random oversampler works. Let me just get rid of this. Now we are simply going to copy paste all the steps we did for splitting, giving the scaling to our data and then training it. We are just going to copy paste the steps with the help of this random oversampled values and then see how our model performs. First with the same value of k as 5, and then we are also going to play around with this value of k and see which k value gives a better result. So I'll just pause this video over here so that you guys are not getting bored, and I'll just come back in a while. Alright, so I am back after copy pasting all the required coding cells from the above cells in order to re-implement KNN on the random oversample data. So what I have done is I have simply copy pasted everything starting from the train test split all the way down till the generating the ROC curve. The only one thing I have changed is instead of passing in the actual or the original data set of x and y, I am passing in the random oversampled value this time. And this is what we wanted to see. How does our model perform by doing the random oversampling? So I even told you earlier that I'll be showing you how we can choose the better value of k and not just randomly guess the value of k. And this is what the coding looks like for this. I'll be coming on to this part a bit later. But right now I am excited to show you what is the final output by choosing the value of k equals to 5, which I haven't changed as we saw earlier without handling the imbalance in the data set. Now it's the moment of truth. What's going to happen? Let's see. I'm just going to run this code and I'm hoping that the value of the recall, precision and F1 score is at least increasing from 0. Let's see what happens. And boom, we can see that we are getting almost 1 everywhere. Over here also this is not perfectly 1, it is just a rounded off value of let's say 0.998, something like that. It's not 100% 1, okay, it's the rounded off value. But we can see that for class 1 our values have increased from 0 to 1, and this shows our model has improved by a lot. Let us also look into how does the confusion matrix and the ROC curve look like. And this is nearly perfect ROC curve which we have obtained, and the AUC value is about 1, and this is just brilliant. Coming on to the confusion matrix part to understand what is happening. So there were 0 instances that our model has predicted incorrectly, that if a particular star is not having any kind of exoplanet, then our model is never expecting or guessing that okay, this particular star will have an exoplanet. So we are not guessing it incorrectly, so this is a good sign. But coming on to this part, where actually there were some exoplanets orbiting a particular star, for 13 such stars we have predicted incorrectly that okay, that this star is not having any kind of exoplanet orbiting it, where in reality it was having at least one exoplanet in its orbit. So now we can bring this number down, keeping in mind that even this number should not really increase. So how we can do it? By playing around with the value of k. So how we can choose the optimal value of k? I talked about it over here. Actually it's not really needed because the amount of which our model is performing right now is really very good. So we can just stop over here, but just for the demonstration purpose, let us say that we wanted to get the optimal value of k. So what we can do is, we can again build the classifier model for different values of k, starting from, let's say I'm choosing from 1 to 10. You can choose any other values to see what is the trend, that how is your error changing with respect to the values of k. But for that we have to understand what is the meaning of an error rate. So what happens is, whenever I'm building my classifier based on a particular value of k, there will be some kind of values which will match with my predicted values from the original values of y, and sometimes it won't. So whenever it won't, I want to get the mean value of it, and that will be nothing but the error rate. So now I am going to see, as the value of k changes from 1 to 10 in my use case, how is the value of k affecting my error rate. Okay, so if I just plot this thing, I am getting this particular curve, and it shows that over here we are saying that the pattern is simply increasing, but at times we can also get decreasing pattern or the a cyclic pattern, and that's when we will be confused that which model, like which value of k to choose. But right now we can see that k equals to 1 and k equals to 2, about it's giving the similar result, but over here k equals to 1 is giving the lowest possible error rate. So we are going to see what happens when value of k equals to 1. We are also going to see what happens when the value of k equals to 10, and let's just see what happens to the confusion matrix. So let us choose the value of k equals to 10 first of all, okay, and then look into our confusion matrix. Obviously we are expecting that it will not perform as better as k equals to 5 value, but let's just see what happens. Yes, again over here the value is 0, but over here we can see that instead of 13 now we are having 24 wrong predictions, that if the exoplanet was orbiting a particular star, we are predicting it for 24 stars that it wasn't really there. So this is something which you need to look at. And now if we pass in the value of k as 1, it must really decrease this value. That's what I'm expecting. Let's see. So we are literally getting almost 111. As I'm saying, this is the rounded off values. We'll be getting 100% over here only and only if this value becomes 0 and this value becomes 0. But we can see we have decreased this value from 24 till let's say 13 till 4, and this is really impressive. Okay, that we are getting only 4 wrong predictions over here now. So this is really very good model now we are having, and that's how we basically choose the values of k. But at times this can really be a pain if this kind of pattern is not observed. So yeah, but this is a very basic idea of how we can choose the value of k, and that's how we can conclude our project for this particular video. But now we are having a particular task for you to do. So we haven't yet applied this model on the unseen data, right, the test data. And the main task for you guys is to see if this particular model is working well on that unseen data. You're going to try it out by yourself, and if yes, can you name any other models that would work better than KNN, and go ahead and try building that model and see if it would work better or not from as compared to what we got over here, right? And if your answer is no, then what could be the possible reason that we might have overlooked in doing this all pre-processing and all the steps? What are few things that we might have overlooked that our model is not performing well on the unseen data? Can you come up with a better model? It's not necessary that you build up KNN. Based on whatever errors you have spot, you can change your KNN to, let's say, you can also go on to the deep learning side. You can try the RNN side like LSTM, GRE, you can try all that stuff and see if it works well with the unseen data. So let's say you are done completing this task, pour in all the hard work and all your time. The question is, how will you send it to us? Because only then you will be getting the certificates once we receive your file. So what is the process you need to follow? So I'll quickly demonstrate this so that none of you is having any kind of doubts. So what you need to do is, first of all, go in the description of this video where you will be finding 2 links. One that will redirect you to this particular notebook, and the second that will redirect you to this Google form where you can upload your coding solutions. But let's say that you are going ahead and checking this notebook, where I'll highly recommend that you do this because there is some kind of code that I'll be changing here and there for the smooth transition and the better way of coding, which I cannot show it in the video because it will really make it more complex and more time consuming in order to explain that thing. So if you really want to see how I code, you can just go ahead and download this notebook and check it. And let's say if you are in this particular markdown cells, over here also we are giving you an option to submit your code. Even if your answer is yes or no, regardless of whatever you will click, it will redirect you to the same Google form. And then coming to this particular Google form, what you need to then do is, please go ahead and create an account on our official website if you haven't already. So just by clicking onto this link, it will redirect you to our web page or the website, and then you simply click on this sign up, and then you just follow the steps which they are asking, and simply you will be registering it, and then come back to this form and fill up all the necessary details, keeping in mind that project ID and project name is unique for each and every project, and its respective details you can find on every project notebook's top part. Over here you can see that I am having the project ID. I'll simply copy this, paste it over here. Similarly, I'll copy the project name and paste it over here, just to make sure that I'm getting rid of any kind of typos. And then simply keep on filling all the details, and also just cross check your email ID, because here is where you are going to get the certificates. If you are going to give a wrong email ID by any chance, your certificate will not be able to reach to you. So make sure that you are cross checking your email ID part. And then again simply go ahead and fill all the other values or whatever detail or information has been asked. And then over here you can simply click on this add file, and it will give you the option of adding your coding solution. So here is where you will be uploading your solutions, and then click on submit. And if you want to see such kind of videos in future about such cool projects ahead, then you can go ahead and subscribe our YouTube channel. And also we would really appreciate if you are having any feedbacks, you can share it in the comments, and do give this video a like if you have learned something and if you have enjoyed this project. With that being said, I'll see you in the next video. Until then, stay tuned.